Mhm.
So yeah, if we could start, maybe walk us back a bit and s- basically tell us what this is. And I think what I'm most interested in particularly is how and why the team decided to put so much effort into this. I mean, I'm glad you did, and I think a lot of people are. But with everything else you have going on, it seems like something like this is often added later, or maybe like a nice to have that somebody might get around to. But it looks like you and the team have really prioritized this out of the gate. So I'd be
Mm.
curious to hear about the thought process that went behind prioritizing the work on this.
Yeah, sure. I mean, the kind of genesis for it, we didn't have, some like crystal clear vision of what we wanted or what we were going to build. I think we did know a few things, right? So, I mean, Jump is a trading firm. Trading systems are very complicated and a lot of things can go wrong. You need to be able to monitor them in a lot of detail, in real time, make sure that you're not sending out too much. So, um, I think there's a lot of history kind of there and understanding, we need to be able to look into these complex systems. That's part of it. Another part is as a development team, I think when we were building the client, we're a little bit struggling to answer certain kinds of questions. One of the questions we had a lot really early on is like, why did we skip a block that we produced? Why didn't it land? Um, Another kind of question we've been trying to answer a lot is why were our blocks not full, right? If the compute unit cap is 50 million and we produced a block that was, let's say, 45 million, why did we miss the extra 5 million? Where did that time go? What was our CPU doing? So there were kind of these advanced questions that we want to answer, and it's really pretty difficult to do this without good tools. So I would say a big part of it is just our development process and trying to speed up iteration and make it so we can build this client really, really quickly. We also have a set of community members that we're building this software that is really, really fast, right? That's kind of the design goal. And it's so fast, it does a bunch of things that most software people run have never done before. So as an example, if you're running, let's say an application, I don't know, an app on your iPhone, you don't need to think too much about what's going on or how that application interacts with your operating system, how much memory it's using, which CPU cores it's assigned to, things like that. But we're building this application, and the validators that are running it actually really do need to understand it. If they don't, fully comprehend what's going on in the software, they're not going to be able to tune and optimize it either. And so, if they're running it on the wrong CPU cores, maybe that's a reason why it's producing smaller blocks. Or if they're paging a lot of memory out as it runs and it keeps going to disk. And, there's a whole bunch of things that can go wrong, and especially with a really, really tuned operating model that software that runs at this kind of level of performance has. Um, we need some way to kind of start to educate the operators and show them the things that we care about. And so I think that was another kind of reason for building the interface is to say, look, there's things we want to highlight and things we want to surface and things we want to try and teach. And so it's a really cool place to kind of start to do things like that.
Thanks. Yeah, I think the amount of information, there's tons of really good information here. And I think one of the reasons that I reached out to do this was to better understand it myself. And I think there are a lot of other people out there who are really looking to understand not only, what's being presented, but how it can be used to do exactly what you said, how to confirm that things are going well, or running as expected, and then also maybe try and pinpoint some areas that things can be improved. So I guess the first thing when we open this up, this is running, it's essentially running by default when you're running the Firedancer client.
Mm-hmm.
Um, and then you're presented essentially with this overview tab. And there are three main tabs. I guess there's an overview tab, a leader schedule, and a gossip tab.
Mm-hmm.
So I thought what we could do first is look at this overview tab, um, specifically at the TPU waterfall, and then also just talk about what someone who's opening this from the first time would expect to see, and like what would they hope to get out of this. I think some of these transactions are specific. Some of this information and the metrics are specific to the validators.
Yeah.
Um, some of it's specific to the network itself. So if you could just walk us through, looking at this for the first time, what
Yeah.
what would you expect somebody to be learning or looking at, right when they open this out of the box?
Yeah. I guess when you first open it, the feeling maybe that I would really want you to experience is like um this feeling of something being alive. Like when you're in the hospital, right, and they hook you up to the little the heart rate scanner that's kind of going beep, beep, and it's like every second this thing is moving and there's sound and it's want you to kind of look at this and know that your validator is like running and that it's doing something and that there's motion, right?
Mm,
And if you open this page and there's nothing happening and none of the numbers are changing, and that would probably be like um the a pretty strong indication that something's wrong. But so here we've opened it and we can see, the chain is progressing. The slot is going up. We're voting, we're typically voting pretty quickly, but maybe we're got two behind sometimes. We're going to be leaders soon, right? And we're counting down. The chain is processing transactions. And so all this stuff is kind of really just there to give you this sense of like security that your validator is moving and it's part of the network, that it's healthy, that it's voting. This TPU waterfall specifically is kind of showing that your validator is able to receive transactions, right, and move them through the system. And so this is kind of called a sand key sometimes. What it's really showing is the life cycle of a transaction from when it arrives at the validator until it maybe makes it into a block or maybe is discarded for some reason. So there's a few ways we can receive a transaction. Typically, people will send them, a user will send a transaction to you over quick. You can also receive votes from other validators via the gossip protocol. And then there's this legacy path with non-quick or UDP transactions. And so you see, the validator is alive. We're receiving transactions. Like these are real users sending us real transactions in real time, arriving at the validator. And they're either getting dropped or they're kind of getting saved for potentially inclusion into a block. So as the transactions kind of move through this system, you see all the things that, the reasons that they're getting dropped potentially. Here are some of the transactions are malformed. They don't look like a Solana transaction, or they're abandoned, meaning someone sent part of a transaction to us and didn't finish sending all of the data. So we had to discard it. Some transactions are unparsable, meaning here we just created some leader blocks, but we can talk about that later. So here some transactions are unparsable, meaning they don't look like a valid transaction. We have a lot of duplicates, which we throw out pretty early, so we're not doing too much work. Some transactions fail to resolve. This kind of means like we couldn't locate the account that they're trying to send funds from, or they were referencing address lookup tables that don't exist. Some transactions expire, which means they were, really old and they're no longer, they couldn't be included in a block anymore. So kind of so on and so on. So there's a lot of reasons transactions might get dropped that aren't visible here. They only occur, they only get displayed if they actually occur. One of the really important ones is if the system is too slow. When we talk about like education, that's kind of one of the really big points we try and touch on, is if the system is ever too slow for the capacity that's, the capacity is too low for the volume it's receiving, we'll highlight that really, really loudly and clearly. So there'll be a lot of messages here saying too slow. We had to drop transactions essentially. We lost some user transactions because we couldn't keep up with the volume we were receiving. So luckily our validator is running pretty well. We don't see anything saying too slow.
So you would actually see a label. The label that a validator would see is actually too slow.
Yeah.
So you would see very clearly that you're not getting transactions through because your system's essentially not keeping up.
Yeah, and the typical one you might see, probably one of the bigger bottlenecks, is verification, right? So this is checking that the signature of the transactions matches the contents of the transaction, that they're authorized to send it. So these, currently you can see where, if you click down here, you can see kind of how busy that this parts of the CPU that are assigned to do verification are, and they're basically idle. We're not receiving many transactions, they're doing almost nothing. If someone was spamming us, or it was a really, really high volume token launch or something, you might see these go up and be really busy. And if they hit 100, it means they can't process, if all of the CPU cores that are trying to verify are fully busy, you might start dropping. And then you would see too busy appear and verify, right? And it would count and it'd tell you the number of transactions you dropped for that reason. And if you saw that as an operator, that's a really good learning point. You're saying, oh, I'm losing transactions, right? It's actually bad for you as a validator because they might have been really valuable. There might have been a lot of money, a lot of fees behind those transactions. And so dropping them is costing you. What you can do is go and, okay, assign more CPU cores to this piece of work, right? Currently we have 6, but maybe you would need 8 or 10.
And these are the tiles at the bottom. These are the tiles that you're looking at. So these are configurable.
Yep, some of them are configurable, some of them are not. So we could kind of go through them. So tiles are just different kinds of work that the system does, and they get assigned to a CPU core. So this system we're looking at, I think, has maybe something like 48 CPU cores. And we're looking at some part of the assignment of it. So, verification, as we said, we've got 6 CPU cores here. That's kind of these little blue dots. Quick, which is the networking protocol that's actually receiving packets from the RPCs or the users and turning them into transactions. We just have 1 CPU core. You can see it's doing pretty well. It has 130,000 connections, just oddly high, but it's only taken around 4 or 5% CPU. You have the networking system here. It's using sockets. I think this is a development machine we're looking at, and it's receiving some traffic. But this thing is pretty idle too. So we can kind of go through the system and look at what's assigned to each of the CPU cores. This dedupe is deduplicating transactions, and so on.
And to your point earlier, these are some of the heartbeats that you were talking about earlier. You're looking here, you're seeing the cores, and these are essentially the heartbeats of the system that are helping us verify that things are running and things are operating.
Yeah, and there's kind of 2 operating modes of a validator, right? There's when you're not leader and you're just replaying blocks that other leaders have produced and making sure that they're valid and that you kind of agree with what they did. And then there's the mode when you're a leader and you get to produce a block. So a lot of, the GUI that we've built is for Firedancer at the moment. So it's reflecting the components that we've implemented in Firedancer, which is the leader pipeline. So there's a lot of work going on around replaying that you don't get to see here because we're not able to visualize it at the moment. But what you are seeing is all the stuff that's happening related to the leader pipeline. So that's why we have this really rich view about receiving transactions. And the tiles that are live right now, the CPU cores that are really running are, the networking. We're receiving all these shreds and transaction data from whoever was the leader. Here you can see the shred tile, which is continuously receiving all of that data, and it rebroadcasts that to the rest of the network. And the proof of history tile is kind of always pegged almost at 100%. That's just part of the design of Solana. It always needs to be hashing in case we would become leaders soon, then it is ready to take over. You can see we're actually about to become leader, and so you'll kind of get to see some of these tiles get busy here in about 5 seconds as they start to do leader work. So now they're a little bit getting busy, and then there you can see pack and bank kind of during that 1.6 seconds did a lot of work. And you can actually click and see these blocks that got produced. And these CPU busy graphs will show you just from the 400 milliseconds that it took to produce that block. So here we can see one of the bank CPU cores was really, really saturated, and the other ones were a little lazy.
When I'm looking at the proof of history tile, I mean, if you saw that saturated at 100, would that be an indicator to possibly assign more resources to that tile? Or is it essentially going to be pegged, the kind of thing that's pegged no matter?
Yeah, it's basically pegged no matter what. And there's a few tiles here that you can't assign more resources to. So pretty much everything in the system you can assign resources, especially, for example, verification, and which is verifying those signatures, and bank, which is what actually executes the transaction when you're a leader. POH you cannot increase the resources. So it's just always going to use one CPU core. The reason is it is just doing this forever loop to do hashes one after the other. So you can't parallelize that. You can't split that work over multiple cores.
I see.
So if you saw this was pegged at 100%, what that could indicate is you're not able to hash fast enough to keep up with the cluster when it's your leader turn. The next thing I would look at if I saw that was, okay, am I producing blocks on time? If my blocks are late because I couldn't do the however many it is, I think 800 million hashes that I need to put into a block in time, then my blocks are going to start being late, and maybe they're going to get skipped by the rest of the cluster at a higher rate than I would expect. And that would be an indication to buy a faster CPU.
Yeah. I did want to come back to something here. When you have buffered, there's buffered toward the bottom, about like 15.7, 15.792, and then there's buffered there at the top. What's the difference between those two?
Yeah, so buffered is a little bit special. So we've talked kind of how the transactions get dropped for different reasons. What also happens to transactions is they become buffered. So if a transaction hasn't dropped, but it also hasn't executed yet, it'll be sitting in the system just waiting until we become leader, right? Those are all the transactions we're gathering and saying, okay, when we become leader, we're potentially going to put them in a block. If you look at the current live view of the system, you can see we have 400 of these transactions, so not very many. The reason is that they expire quickly. The transactions last about, I think it's a minute or less before they expire. So you'll see this can't go down if we wait another 30 seconds or so. These will move from being buffered into the expired section, which means they're no longer eligible and they have been dropped. But so when we're becoming leader, let's say we had 30,000 transactions available, right? They were pending, we call them buffered, they're waiting, and they could potentially be packed into the block. We can't put that many into the block. So what our system is going to do is it's going to go through that list of buffered transactions and pick the most lucrative ones, kind of one by one almost. The scheduler is actually very sophisticated and does a lot more than that, but at a simple level, that's kind of what it's doing. So it goes down one by one and puts them into the block. And you can see here it packed 1,994 of them into a block. But there's a bunch of them left over. So those stay actually in the buffer and they'll be available during our next leader slot. So that's kind of what it's saying here is when we began this leader slot, or when we began the time building up to this leader slot, we had 16,000 transactions buffered. So those were an input to the system. And when we ended the leader slot, we had 22,000 buffered. So actually during our leader slot, we increased the number of transactions we were holding. The reason is that, well, we packed 2,000, but we received, 400, almost 440,000. So there was a big imbalance and the buffer grew. You might say, well, it only grew by 7,000. Why is that? But, this thing kind of nets out to zero. Everything adds up. So what happened is we just dropped a lot of the stuff we received. A lot of it was duplicates. A lot of it was unparsable. So, only 7 to 10,000 of them actually made it all the way through to the buffer. And then we dropped, then we packed some. So, yeah.
And then the 15 or almost 16,000 buffered, that was the holdover from previous blocks.
Yeah, so you can see here, so we ended this block with 22,748 buffered, and that should be the input to the next block, right? 22,748. And so this output here, 23,243, is again the input to the next one. So these buffered will just hang around, kind of, they'll keep flowing into block after block as being available until eventually they're going to get expired. And you can see here, well, we probably expired those ones we were looking at earlier, but we received a bunch of new transactions. So we actually grew the buffer.
Right. If you could go back one or two blocks. Right. So if we're looking at this end to end, we received about 15,000 transactions, and essentially of that, like 1,568 packed. and about 200 failed, and about 1,400 made it through, if you trace
Yeah.
it kind of from beginning to end. Okay.
Yep. And there's two kinds of failure here that are interesting to point out. One is failures that don't make it into the block, which we call unexecutable. And then there's failures that did make it into the block, which are just these failure. So these failed transactions paid their fee. They went into the block and they were, shown as being failed. They got charged. These ones weren't even chargeable. The main reason something is unexecutable is if it's already been executed. So some prior leader already executed that transaction and we kind of didn't realize that and we tried to execute it again. Or there's a bunch of kind of other reasons. The fee payer doesn't have enough balance. Like they tried to said, oh, I can pay 100 sol for this transaction, but then they didn't have 100 sol. We want it, yeah, we'll go try execute it and say, oh, they don't have balance, and then we have to throw it away. So there's a lot of reasons for that kind of distinction. But in general, yeah, you'll see we try and execute a few things that don't end up making it in.
Okay. And is there anything, we talked about the too slow earlier in the life cycle. Is there anything that might show up, like in the buffered section, that would indicate that, we're buffering too many, or, we're just not able to get as many through as we would expect to get through?
Yeah, so we set the buffer size to, I think, 65,000, around that. And if the buffer fills up, you'll see another little message pop up here saying, I think buffer full. That isn't really a cause for concern because the buffer smartly keeps the most lucrative transactions around. So if it becomes full, it'll just drop very low value, like almost worthless transactions. And so it's, those would never end up making it into a block anyway if you had 65,000. I mean, remember, when you're leader, you have 4 of these slots, and each of them we're packing around 1,600 transactions. So you're getting about 6,400, maybe up to 8,000 transactions during these 4 slots. So if something is ranked like the 40,000 most lucrative transaction in your buffer, it's already probably not going to make it in. So it's totally fine to drop those. We set it that high at 65,000 mostly for certain rare cases where a leader might have multiple leader rotations right off one after the other, in which case they might spend down their buffer a little more.
Okay, I had something else, but I lost it. So really, like, it's really up almost in the first half of the life cycle, where if a validator comes in and starts seeing messages like too slow, or I think you mentioned one other, that's where we would expect to see these warning messages popping up.
Yeah,
the validator would want to keep an eye out for, or an operator would want to keep an eye out for. Okay.
Yeah,